Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, we are very happy to have with us Kevin Fu, who's an associate professor at University of Massachusetts Amherst and will be soon joining University of Michigan at Ann Arbor. Kevin is very well known for his work on security of medical devices. He's won the TR under 35 Researcher Award. Today he's going to telling us about implementing secure protocols on embedded devices.
All right. Thanks for the introduction. I think this might make perhaps my fifth talk here. I think I do this on average about once every 1.5 years. So it's good to be back again. It's always a pleasure. So this is and in case you hear mumbling or voices in the background, Amir Rahmati is on the Skype line. So he's joining us, and his booming voice is over the speaker system. He's the lead student on this project. His name is in bold here. He'll be presenting this at USENIX Security next week. So if I make any mistakes, he may pipe up. Are you still there, Amir? Okay. Anyhow, I'm sure he'll be back. Anyhow, so what I'd like to present today are actually two talks, depending upon how much time we have. It was 1 hour, is that correct? 1 hour. So I'm going to talk, first of all, about interesting things to do with SRAM. So SRAM is a kind of memory that's found on pretty much every kind of digital logic in the universe. It's how we implement L1 caches. It's how some microcontrollers implement their RAM. And we're going to use SRAM to do some unusual things when energy is one of our constraining factors. Okay, so and this is joint with Amir at UMass, Mastooreh, or she goes by Negin, who was an intern here last year in G. Lou's group, Dan Holcomb, a PhD student at Berkeley, Jacob Sorber, a new professor now at Clemson, Wayne Burleson, who's a VLSI design engineer at UMass. Okay, so what's the motivation here? There are a lot of devices out there that don't have access to a trustworthy clock. One large class of devices that fall into this camp would be batteryless devices. Anyone use the Orca card? Okay. Almost everyone here has an Orca card for transportation payments. And as you can imagine, there's no battery in there. And because of that lack of battery, it doesn't know what time it is. So there's no notion of time. While the card is being powered up to do a payment, it knows how much time is elapsing during a transaction, but it has no idea how much time has elapsed between transactions. This is also true for passports, employee ID badges like this one. They know exactly how much time has elapsed when you're using it, but they're completely ignorant about time because time is fleeting, but we need to keep control. All right. I'm going to try to insert as many 80s and 70s references as possible in this talk. So what do they have in common? Again, no long-running clocks, and the adversary controls the power and the time. Whoever is powering up the device gets to choose when to shut it down. And these devices hold information that you probably don't want to leak. It could be private information. And so this has led to a number of security vulnerabilities by researchers across the globe. I'll just highlight a couple. It'd be difficult to enumerate them all. But there was one recent paper on dismantling the MyFair Classic. This is a contactless smart card. It was used, I believe there are billions of them in circulation at the time. And it's a payment card mainly for transportation. And they found that using a brute force attack, they could extract all the information to effectively clone the card. This attack has been replicated in other contexts, the London Oyster card, which I hope is working successfully now with the Olympics. And there's just more and more papers coming out as the industry fixes the card, somebody finds a new flaw, typically exploiting this encryption oracle. Because you can query the tag basically an infinite number of times, you can extract all sorts of information. And the card is really none the wiser. It doesn't know how to rate limit because it doesn't have a sense of time. At best, it can just set a counter and say, well, I've been queried a lot. And oh, don't forget San Francisco. Okay. All right, so moving on to slide 4. this all basically boils down to brute force attacks affecting these time unaware devices. This could be side channels power analysis, DPA, for instance, pioneered by Paul Kutscher's group. Simple reverse engineering, sometimes if you don't know what the algorithm is as implemented, if you query the tag a sufficiently number of times, you can start to deduce what the algorithm is. And then just plain old brute force, guessing keys. And the problem is there's no speed limit today. So we're going to try to stop that using our time machine we call the TARDIS. In our threat model, what we consider are what's called semi-invasive attacks. This is a term, I think it's more familiar with the CHES community, the cryptographic hardware and embedded systems community. What this means is the adversary can interact with the card from the outside, but we're not going to consider an adversary who's able to, for instance, physically drill into the tag or inject ion beams. But we are going to worry about outside attacks like heating up the card and cooling down the card. OK. So to give you some more quantitative information on just what's going on when people attack these systems, here are 5 example papers and just how many queries it took each of these attacks to break the security of the system. And by break, I mean have enough information to clone a card. So here ranged in simplicity to more complexity. Shamir broke the UHF password. These are supply chain RFID tags. It only took 200 queries to be able to brute force guess the password. It takes about 2 seconds. If you work up to some of the more interesting things, over 10 years ago, Ian Goldberg and I think David Wagner had reverse engineered some things in the GSM SIM cards in phones and were able to duplicate those SIM cards using about 150,000 queries. If you do 150,000 queries, you could extract enough information to duplicate a SIM card. And these problems are appearing again and again and again. So our contribution here is a way to restore some sense of timekeeping, and we're going to do that based on SRAM decay. These are the decay of one of the most common circuit elements found in digital logic, and we're going to exploit how this digital logic behaves over time when you remove power to create clocks, or clock-like devices. So I'm not an EE. This is going to be the most EE slide of the whole talk. I think my rule is only 1 transistor per talk. I apologize, there are 4 here. So this is an SRAM cell. Each SRAM cell consists of approximately 4 transistors. It has 2 other transistors to do some of the control logic. But as far as you need to know for this talk, a SRAM cell is a cylinder. And they didn't teach you that in VLSI design? So an SRAM cell is a cylinder, and it contains either a binary 0 or a 1. This is the atomic unit as far as most computer scientists are concerned. Now, when you remove power from this digital logic, it starts to decay, and it goes away. And it enters sort of an unknown state. And then when you power back up, it's going to power back up to one of 2 different things. You can probably guess. It'll either power up uninitialized as a 1, or it'll power up uninitialized as a 0. The interesting thing about SRAM is most of the bits tend to be physically random in their initialization and how they initialize after being powered off. Not all of them, but the vast majority of the bits behave in that way. And we're going to try to exploit that to create timekeeping. So luckily, our computers today have more than 1 SRAM cell. So if you have a large collection of SRAM, say 240 bytes is what we use, you can start to do some interesting statistics. And you can count, for instance, after your system boots back up, and you would like to know, if you'd like to know how much time has elapsed during that downtime, because that's what the adversary is trying to exploit to trick you, you just count the number of SRAM cells. And you look at their values, and you see how they differ from the values that you initialized. And by counting them, you can begin to essentially dead reckon how much time has elapsed. So to give you an example, we took a photograph of a different TARDIS, and we put it into our SRAM memory, and then we would power down the system. In this case, we powered it down after 150, 190, and 210 seconds, and then see what the picture looked like after we powered it back up. So these are real experiments here. Happens to be on an MSP430 microcontroller. And we split the picture up actually into 4 pieces because it didn't fit into our memory. So this is actually 4 pictures assembled into one. But after 150 seconds, you can see there's a little bit of pixelation. The memory is starting to degrade. Again, we powered it off, we powered it back on. The TARDIS was still there, but it was beginning to dematerialize. At 190 seconds, you get some significant degradation of the image. And at 210 seconds, it looks, to me, almost statistically random. Question?
Were you using bitmaps or JPEGs?
The question is, were we using bitmaps or JPEGs? Hey, Amir, do you happen to recall what we were using?
Hello?
Yeah, hey, Amir, do you happen to recall, was it a JPEG?
I don't have your audio anymore.
Oh, okay. But we translated it into bitmap, I believe. I'll have to double check on that. Yeah. So what you can do, though, with the image is you can start to go backwards. If you take an image, you can try to guess how much time has elapsed. So for instance, if you see this pixelated image and you kind of put it next to all your different sample points, you can kind of guess, well, you know what? It's sort of in between the 190 and the 210. So I'm going to guess that we were off for between 190 and 210 seconds based upon that memory decay. So that's the intuition of the mechanism we're going to use to create these trustworthy local clocks that are unpowered. No batteries necessary. It's just running off the power that's remaining after you turn the system off. Okay.
Is this temperature dependent?
It is very temperature dependent, and I'll be getting into our temperature chamber measurements.
These properties change over long periods of time. Like if you repeat this experiment a year later, would the units on the x-axis stay the same?
So I don't have any, so the question is, do these results change over time? And I believe the industry has a term for that. MBTI, I believe, is the term. Essentially the degradation of circuits over time and exposure to heat. In theory, there should be some degradation. We haven't seen any. And SRAM, as far as I know, is more resilient than, say, flash memory. Flash memory does wear out. SRAM doesn't have that type of wear out property. So we haven't seen any, but there could be some. All right, so let me go over the TARDIS algorithm and how we try to dead reckon and guess time on our device. So we initialize SRAM. We, in our particular implementation, we reserve about 240 bytes of the SRAM to do this. And we happen to just initialize it all to 1. You could choose all zeros if you'd like. You could choose a picture of your favorite cartoon character, whatever you like to do. But we chose all 1s to simplify our algorithm. Now, when the power turns off, the SRAM cells begin to decay. So when we power back up, we just compute that decay. We count the number of bits. But as was asked, as was pointed out just a second ago, what about the effect of temperature? Temperature will affect how many bits are decaying when you have time as a factor. So we need to compensate for temperature. And the way we do that is rather simple. So after we boot back up, we compute the SRAM decay, and then in order to use essentially the right curve, that is the right interpolation results, we measure the temperature. It turns out most microcontrollers have onboard thermal sensors, so it can measure its own temperature. And for the computers that don't have a temperature sensor, almost everything out there is actually a temperature sensor, it turns out. It can behave like one. So we measure that temperature, and that way we can figure out which curve to use in estimating the time delay. After we do that measurement, we initialize the SRAM again to a known condition so that we can prepare for the next power off. Of course, there is a very definite temperature range, and in our case, we're using a very simple algorithm, but you could use a lookup table based on different temperature measurements for profiling your chip. If you want to be really fancy, you could use curve fitting. Right now, we haven't found it necessary to do any kind of fancy, like closed form solutions for computing how much time has elapsed based on temperature. And hopefully, you'll see why in a moment we didn't choose that pathway.
So it doesn't matter to which state you initialize. So for example, if you initialize to all 1s, would that give better results or worse than to all 0s?
Well, I'll get into that data a little bit, but it hasn't affected the statistical properties.
Okay.
What it does affect is what's known as leakage current. So it essentially speeds everything up. Oh, so what are the other factors influencing the decay of SRAM? There is temperature, but there's also capacitor size. It turns out, as I was explaining over lunch to Stuart, if you think back, has anyone taken an EE sort of 101 course? Probably most people are required to if you took. Okay. You may have recalled things like Thevenin equivalent and all that fun stuff. Basically, you can represent any circuit as a series of the fundamental discrete parts, one of those discrete parts being a capacitor. And it turns out all circuits have some non-zero capacitance, and we're going to exploit that. But there's also variation across chips, so we'll explore that a little bit. I don't have time today, well, at least I wasn't planning to talk about SRAM size on its impact. So as to the question about the thermal setup, this is how we ran the experiments. I think the pictures are pretty clear up there, slide 13. What we have is what's called a thermal chamber or an environmental chamber, and this allows us to precisely set the temperature surrounding the chip that we're doing the test on. We have our infrared thermometer up there to help us gauge the temperature, which is a fairly precise thermometer. And then we're using what's called the Texas Instruments MSP430 as our experiment chip. It's a microcontroller, and it has on-chip SRAM. And then over there we have a DAC. The DAC is helping us to precisely control when we turn on and off the power. So in other words, this is our programmable power supply right here. So we can get ground truth, in other words, over how much time has actually elapsed. So to give you a feeling of just what kinds of time can you measure using just SRAM decay, here's a rough chart. I'll show you some more detailed data points in a moment. But what you'll find is there are basically 3 phases of time. I like to think of the TARDIS as an hourglass. So in stage 1, you've just lost power, and so all the bits are intact. And if you were to power back up very quickly, you would expect to see all the bits there. But there's a magic threshold for this particular case and this particular temperature and this particular capacitor. It happened to be around 150 seconds. At that point is when SRAM cells began to decay, but not all instantaneously. They all decayed at different points in time. So that's when you enter the second stage, where you can get some more precision in terms of how much time has elapsed. But it's a relatively short sliver of time, and for that reason, at the moment, we're not exploiting that sliver. At the moment, we're only exploiting the TARDIS to give us 1 bit of time. Has the hourglass expired or not? And that's what stage 3 is. So at stage 3, in this case, around 230 seconds, that's when all of the SRAM cells have decayed. And so we have no way to distinguish whether it's been 250 or 400. We just know it's been more than 230 seconds at that point in time, just like an hourglass. OK. And again, this was with at room temperature and using a 10 microfarad capacitor, which is relatively common for smart card applications. OK. So how about capacitor size? We tried all sorts of different capacitors to try to see how that would affect it. It turns out really temperature and capacitor size, these are all proxies to what we're actually measuring. The real causal effect is what's the current voltage on the voltage supply. And the capacitor is going to give us a different voltage depending upon its capacitance. So with no capacitor at all, we're typically able to get on the order of just measured in seconds of time. For security applications, we have found that to be sufficient because it allows us to stop these queries. You know, what previously could have been thousands of queries per second, so we can slow them down to 1 per second using this timer. But if you're on a smart card, you're likely going to see actually a built-in capacitor because it's got to store its energy somewhere when it's harvesting energy from RF. You'll typically see it around 10 microfarads. Then you can get up to minutes. On some more advanced sensor devices like Josh Smith over at UW had a WISP sensor with a supercap, and the supercap was about 10 millifarads, I believe. And there you can get a timer that lasts many, many days without actually having to power the timer. It's just working off the leakage of your SRAM. OK. So here's some more detailed measurements about temperature. And so each one of these data points is a measurement where we had to run that thermal chamber, get it to a precise temperature, measure it to make sure it actually was that temperature, and then use the DAC to power it up for the precise amount of time for that particular measurement. And as you can see, in all cases, even when you crank it up to 50 degrees C with no capacitor whatsoever, you still get a measurable delay. That is to say, you don't need a capacitor in order to get any kind of interesting measurement. So here we're down at a fraction of a second when we've heated it up to 50. But at room temperature, we're getting about, where are we? Looks like we're getting up to about 2 seconds at room temperature with no capacitor at all. A question?
So does that continue to scale, or beyond 50C, does it start to melt?
Oh, the question is, does it begin to scale with temperature? The interesting thing is, I've forgotten the exact temperature when the chip fails. You can continue to heat it, but at some point, you've just destroyed your chip. So we take advantage of that in our adversarial model because you can't go to infinite temperature. You can try to go to absolute zero. Luckily, we don't need to worry about freezing attacks here. Freezing actually helps us. It slows the timer down.
Could you go 1000C or 500C? How far?
I believe, hey, Amir, do you recall what the maximum temperature without causing permanent damage to the MSP 430? I think it was on the order of like 200 degrees Celsius.
The spec sheet says 120, if I'm not mistaken.
Okay. Question in the back.
Very simple. Maybe I missed something you said. So why is the y-axis stopping at 50-something%?
Oh, so why is the y-axis stopping at 50%? That's actually a good question. SRAM, there are two large classes of memory, SRAM and DRAM. In SRAM, bits decay to effectively statistically random. So you're going to see 50% 0 bits and 50% 1 bits, and that means decay, even though you set all of your bits to 1. Now, if you were to ask me that question, and if I were Alex Halderman, I'd give you a different answer because he did work on DRAM a couple years ago, I think, Remanence Decay in DRAM. And DRAM is the external memory. So SRAM, think of it as L1, L2 cache. The DRAM, think of it as the SIM cards you buy at the shopping store or whatever. Those have capacitors rather than transistors to save the digital state, and they do go to 0, all of them. So here we have to distinguish from random. Makes it a little bit harder. Question in front.
So is it feasible to trick is the thermostat close enough, the thermistor close enough to the CPU that you could have the thermostat read 50 while the chip itself was at, while the SRAM was at 28?
All right, so the question is effectively, is the temperature sensor, can the adversary trick the temperature sensor, or trick the CPU without tricking the temperature sensor because of maybe distance between the two physical components? I don't have an answer to that other than I know from thermodynamics that you're not going to have instantaneous heating. The chip itself, the silicon, is small enough that it's hard to see with the visible eye. The packaging is large, and it's mainly just the leads going to the pins. But the actual silicon is only 3,000 logic gate equivalents. And if you think about how small transistors get today, 3,000 logic gates is in a very small area. So I don't have evidence. I would love to meet someone from the thermodynamics community to help me give you a formula. But my gut suspicion is it would be really hard to heat one part from a micron away from another. But that's my suspicion. There may be a way using a non-semi-invasive attack like ion beams or some very targeted radiation, I suppose. But that's outside of our threat model. We're trying to up the ante here. We're trying to take an existing card that has known vulnerabilities and make it harder to break. Okay. Anyway, you can do this on all sorts of different temperatures, and you're going to always see a curve. The temperature is basically changing that magic inflection point where the decay starts. So as you heat up your memory, the timer will run out more quickly, so you'll have shorter timers, but the timers are all non-zero. And that's our goal here, to get something greater than 0 for a timer from a security perspective. There's also naturally some chip variation. All of our tests were done on the MSP 430. However, we did see variation even between individual chips. It was difficult to control the temperature perfectly. We only had about a 2-degree precision on our thermal chamber. It's designed actually to have a much larger range, but we weren't allowed to install liquid nitrogen tanks in my lab. So we could only basically do heating. But as you can see, there is some slight variation. The important thing to note is the shape of the curve is always the same. So in this way, we could train on one chip and then use that for the other chip and still have some relatively good precision.
Going back to the memory, so if you were to start with a random initial configuration, then you probably want to go somewhere higher so that
Okay, so the question is, since the natural decay is to the statistically random case, what if you initialized memory to statistically random?
Not go to random given the initial condition, right?
Right. So, well, we kind of ignore that. I mean, the way we get around that is we initialize memory to a known pattern. So that way we can do a delta, basically XOR, and then count. And we know the closer we get to 50%, the closer we are to an expired timer. There may, I would imagine there could be some fancier algorithms to try to squeeze more information. It'd be really interesting to see if we could do better than this. There's some, you can actually profile each individual SRAM cell. I'm not sure if you're going to be able to exploit that extra information to get much more than a small constant factor better, but maybe you can. About I think it was about 4%, a small percentage of the bits always come up as a 0 or always come up as a 1 because of slight mismatches between the lengths of wire and the way the transistors are connected. You might be able to do something interesting there, but identifying those bits, since they're only a small percentage, might not be worth it. It's more code space. Okay. So we implemented this on our favorite platform of choice, the UMass Mu. It's a computational RFID tag that we've manufactured in our lab. It's based on the Intel WISP, or I guess the UW WISP is what it's now called. But we augmented it with a slightly beefier processor, so we call it the Mu. We also augmented it with these little piezo elements, so it can make little buzzing sounds, sort of tonal things. So we did this in order to try to test the theory of could we make a squealing RFID credit card that squealed when you queried it too much? Because naturally, if somebody's querying your credit card in your wallet, 100 times a second, that probably is not normal unless you're a really fast shopper. So in this particular device, we measured the execution time, and we found that we could get about a 12-second timer with a standard deviation of about 0.1 seconds. So if you query it faster than once every 12 seconds, we're able to then make the tag beep, and it acts as an audible alert to say something fishy's up in your wallet. It doesn't solve the problem, but at least makes the wallet bearer more aware of their surroundings. And we have some other applications that are in our full paper, such as e-passports and other batteryless devices. So going back to the table, again, here's that original table from the beginning of the talk about how many queries it took to break these various systems, ranging from car immobilization to payment cards. And you can see they range from about 2 seconds to 8 hours. And so if you assume an 8-second TARDIS to slow down each query, then it moves to a much more interesting minutes to days. So in some cases, you're actually seeing a 100x increase in the amount of time the adversary needs to spend to get those same number of queries taken. So this doesn't solve the security problem, but it significantly raises the bar to the adversary such that there's more chance the adversary will get noticed or exposed. And it also comes at no physical cost. There's no change to the circuit here. This is just a software update to the existing program running on the device. Okay, but there are ways to attack the TARDIS. And the two most obvious ways, at least to us, were cooling and heating, because everything is about temperature here. Because we're semi-invasive, those are the main attacks we worry about. The good news is, for cooling and heating, the thermal sensor seems to make it much harder to mount these attacks, especially if you're talking about 1-second timers. Being able to heat and cool a tag very quickly within a single second we think would be difficult. There is this other attack we haven't solved. We call it the pulse attack. This is where you're pulsing, heating, cooling, heating, cooling, heating, cooling, heating, cooling, in an attempt to wear down that timer, but then by the time the sensor reads the measurement, it's back to the normal temperature, and so it's none the wiser that not enough time has elapsed. This probably would affect timers that are on the orders of minutes to days, where you can actually do a pulse. But for a timer on the order of a second, I would like to learn more, but I'm not aware of any way to heat up a tag with that kind of precision, sub-second precision. There may be a way, but I'm not aware of one that I could just carry in my back pocket. Lathes? What? Lasers. Lasers? So.
Seems like a natural solution to heating anything, right?
Possibly. The problem, though, even with a laser, don't forget, It's not about precision of aim. Once you heat it, how long does it take for it to cool back down again? Yeah, so yes, you could use a laser to try to heat things up. In fact, we have found that just running the card heats it up by 2 degrees centigrade for each trial. And we had to wait. Amir, do you remember how long we had to wait between trials to get the card to cool itself down? I might have lost him. But I think it was on the order of oh, hello? I think it was...
In the thermal chamber, it took about like 1-2 minutes for it to cool back down.
Yeah, so just trying to compensate for its own computation took about 2 minutes to cool it back down. I'd be surprised if you could get like a liquid nitrogen or piece of ice to cool it back down in less than 1/10 of a second, given that it has this plastic housing. But again, we're talking about semi-invasive attacks. If you're going to bring in Sergei Skoroborov from the UK, from what is it, Ross Anderson's lab, he can do anything. He can extract AES keys from stones. He's outside of our adversarial model here. We're just trying to increase the difficulty and the amount of time it takes. Yeah.
Did you talk about exactly the defense mechanism? Like, so for example, what would you do? Like, do you actually keep a counter in memory, or do you measure how random the bits look like when you get power back? What's the details of the defense here?
So the actual algorithm is in the paper, but I'll just give you the high-level picture. The high-level picture is we look to see if enough bits have decayed. And I think I mentioned in the beginning, we don't use a closed-form solution in our implementation. We could try to find a polynomial that represents that lovely curve. But because most of these devices are closer in spirit to RFID tags than desktop computers, there's not a lot of CPU available to do that kind of computation. For instance, we don't have hardware multiply on our platform. So instead, we chose the more simplistic approach of just look it up with a very small number of data points. This gets us a 1-bit timer, essentially. So we know how much time would elapse for a given temperature, whether it's expired. There's a lot more you can do if you have more CPU or if you have more space. Anyhow, with the pulsing attack, I do think it's a real problem. But we're relying on physical limitations for those short timers, the laws of thermodynamics and how quickly you can heat and cool. And you can also, if you really cared, you could buy these things called thermal fuses. In fact, I believe for some FIPS 140 devices, this is what they use to detect if you maliciously took your CPU and froze it. It will cause the chip to fail if you do funky things with temperature. But we're trying to stay away from modifying the circuit because that costs money.
And to clarify the algorithm, you count the number of bits, and if it's below or above, below the threshold or whatever, you just say, no, I'm not going to answer your question.
Exactly. Exactly.
Wouldn't it be safer to alternate have the odd bits need to be 0 and the evens need to be 1? It seems like you might have an electromagnetic pulse type attack where there's some way just to attack to put ones in all of the SRAM. And if you're worried about that attack, then
that's an interesting
0-1, 0-1 is the way to go.
So the suggestion here is instead of using the 1-1-1-1-1 pattern, use alternating 1s and 0s to defend against EMP attack that may cause all the bits to flip in one direction, is what you're saying. It sounds like that would be a no cost from an implementation standpoint, so why not? But I'm not familiar enough with the EMP to know how resistant it would be.
It sounds cool, though.
Yeah. An EMP-proof TARDIS. That would be great. Okay. All right. Moving on. Okay. So the main application I talked about today was defending against brute force, sort of treating smart cards as encryption oracles. But there are other applications you can begin to imagine where this timer might help. We're not sure, but it's areas we'd like to explore. So being able to implement timeouts and authentication protocols, especially with RFID tags. RFID tags don't know how much time has elapsed before it gave a challenge to a reader. Now it might actually be able to implement a sense of time where it says, hey, you had too much time to think on that one. Maybe you cracked it, so try again. Maybe you could also implement things like temporary ownership. If you think back to the resurrecting duckling problem, this may be a way to bring in, oh, I'm sorry, from the look on your face, not everybody is aware of what the resurrecting duckling problem is, so let me tell you what it is. I'm sorry, I'm going to forget the student's name, but I know it's from Ross Anderson's group. Was it Richard Clayton? Okay, but a number of years ago, they proposed the following solution. How does a new duckling know who is his or her mother? Well, when you are born, you look around, and the first thing you see is your mom. And so that's how they said that's the resurrecting duckling problem. So the way they're going to solve it is when you lose all state, the first person you see, well, that's your owner. Or that's who has the authentication controls of you. And so in some sense, RFID tags are this way. Whoever first sets the password is the owner. All right. There's also the double tap and passback attack where this might be able to help. This is where somebody's double charging your credit card. Now you might actually be able to know if somebody's double charging it. Or passback, this is when somebody behind you is sort of doing this and you think they're being friendly, but they're actually just getting your RFID payment card. On the non-security front, there could be some interesting applications with ultra-low power sensors. So sensors today may implement what's known as a real-time clock. This is a clock like we normally think of clocks. It's always ticking. The problem is you're paying for each clock tick even when you're sleeping. And so if you were to replace that real-time clock with something like the TARDIS, now you wouldn't actually have to draw any power while you're sleeping. And so this may replenish the energy that you've been wasting on a clock that you're not using. The disadvantage is you end up with a coarse-grained clock as opposed to something that has microsecond granularity. But for some sensor applications, you might not need that kind of precision. And I already mentioned the e-passports. There was some interesting crypto research, mainly in the 1990s. I saw there was a recent paper by Salil Vadan and others at Harvard on time-release crypto. It's not directly related, but it may actually trivialize the problem because it allows you to sort of insert a known quantity of time into computations. So in time-release cryptography, the problem was how do you make sure someone cannot open a message for a given amount of time? And most of the solutions have to do with proofs of work or computation. The problem is people have different computing powers, and so the constant factors were tremendously large in between what Alice or Bob might be able to compute, and therefore one might be able to cheat the system. But okay, moving on. There's quite a bit of related work in this space, in particular with data remanence. The most interesting work would have been this data retention in SRAM. So Peter Gutman at USENIX Security in 1996 and Sergey over in the UK did quite a bit of research on just how long does SRAM hold its contents. And they have quite a bit of temperature data on how long the SRAM holds its contents. And actually their work inspired some of our ideas. We combined this with the Ferns approach here at the bottom. Dan Holcomb, one of the students on the paper, had created what's called a PUF, a physically unclonable function based upon SRAM decay. It turns out some of the bits always come up as 1, some of the bits always come up as 0, and he was able to identify individual chips just by how the SRAM powers itself up. And so that was sort of our inspiration for the TARDIS and thinking how else can we use SRAM to do interesting things. Alex Halderman had a very interesting paper in 2008 at USENIX Security where he showed how you could recover the contents of DRAM even if you take that RAM module physically out of the laptop, you keep it frozen, and you physically take it out of the laptop, plug it into a new laptop, you power it up, and guess what? It still contains the same bits you set. That was on DRAM, again, a different kind of memory technology, but it's similar in spirit in that it's all about remanence decay. There are plenty of other clocks you might consider using. Lamport clocks from the 70s, you could try using that. But again, here we're mostly about trying to install some kind of physical notion of time into the computation. All right, so to conclude, basically 4 points, of which I hope you take home at least one. The TARDIS uses the remanence decay of SRAM in order to estimate time. We use it as a 1-bit timer, although you could try to use it for more than 1 bit, depending upon your application. The TARDIS makes brute force attacks harder. It doesn't eliminate them, but it does make the attacks harder in that it takes more time. The beauty is that it's pure software. There's literally no change at all to the hardware. So a manufacturer who creates a smart card could literally just update their firmware with this very small algorithm in order to have a sense of time. to defeat these very simple Oracle encryption attacks. And the other interesting thing, at least to me philosophically, is this is one of the few cases I'm aware of where we use remanence decay for good. Most security and privacy researchers think remanence decay is bad because it means privacy leaks. You can violate privacy. But here, we're using it to actually improve the security of our system. So let's see, it's 2:20. I've forgotten how long we have until 2:30. Okay. So I think I'll take questions now. I do have some other material I'd be glad to talk about that has to do with other interesting things you can do with SRAM in order to make puffs. But I can talk about that later as I see the crowd thinning out. But I see we have a question in the back.
So what's the smallest amount of SRAM you need for these techniques to work?
The smallest amount of SRAM, and Amir, please correct me if I'm wrong, we found is 240 bytes. But one of the students, Dan Holcomb, told me that he could get something useful with as little as 1 byte. Is that correct with your recollection, Amir? Are you still there?
We use 240 bytes, but you can do with much lower memory, or smaller memory.
Yep. And actually, maybe I'll have a follow-up question to your question. The natural question to ask after that is, well, does more SRAM help? Does it give you a more precise timer? And that's what I would have thought. It does help with more precision, but it comes at a really big cost because every additional SRAM cell you have increases your leakage current. And what this effectively does is it drains your energy faster, so you actually get shorter clocks if you have more SRAM. So there's a sweet spot where you need just enough SRAM to get the precision you need, but not too much because then your timer is going to be really short. Okay. Question?
So the platforms you're targeting, do they have any form of permanent storage when they're powered off? Or
the platforms we target do have permanent storage. So I've talked with smart card manufacturers and like the guy who invented the Java card, and they tell me, yeah, there's non-volatile memory on there. In ours, we happen to have NOR flash memory. I've forgotten how much. It's something on the order of like 10K, I think. Anyhow, small. Non-volatile memory is extremely expensive to add to a device. So it'd be nice not to have any, and it would reduce costs. SRAM is a relatively large chunk of circuit. This is why your L1 cache is limited. You're not going to have gigabytes today of L1 cache because it would take up too much space on the die. So that's one of the limitations.
I just wonder, in terms of if you wanted to implement a timer, if you just did some operation that you know takes a second on the device and kept track of how far you've gotten, would that be enough? Or like to some number of digits?
Well, let's see. Yes, but can you do this when you're powered off?
Oh, but you keep track of how far you've gotten, and next time you power up, you say, okay, I was previously at digit 40.
Okay.
I need to do 60 more before I'll give it.
So is there a way you can use non-volatile memory to make a more interesting timer? So actually, that's how it's done today. So manufacturers do invest in small amounts of non-volatile memory to store counters. They're called transaction counters. So I forget if it was Visa or MasterCard, but one of them has a transaction counter. And after you have, I think, the card we tested, this was 5 years ago, after you do 10,000 transactions, it just stops, and you have to get a new card. I call that a denial of service attack.
But this would implement the rate, not just the counter, right? So it's
Exactly.
Yeah, what you're suggesting.
So counters can give you a physical total limit if you think about integrating over all time. But the nice thing about the timer is now you can have this card work sort of infinitely long, but for any given period of time, you can bound how many queries happen in a given period of time. A counter alone is not going to be able to do a time bound.
I think the solution he's proposing would implement the rate also, not just the counter alone, right?
Oh, you mean combine the two?
Not combine, like his solution is different than TARDIS, if I understand correctly. And the idea is you know what the time is somehow, and you start computing, performing the computation that's very predictable in how long it will take. And it has regular periods where you snapshot the state of that computation. And you know if you've done 3 rounds of that computation, then it took this long. You've sort of lived this much.
Right, except the processor's not running when the power's up. So it's solving a different problem, I guess.
So you would just say,
That would tell you how much uptime you had.
yeah, then
It could tell you uptime.
yeah, so you could say, I'm going to rate limit. You have to give me this much uptime before I'm willing to answer another.
But how is that different from a transaction counter? Maybe that's more floating point, that's more probabilistic.
Well, it guarantees a minimal amount of time between increments of the counter, right? The transaction counter just says.
So depending on, I mean, suppose you want to watch, implement this, I'm going to allow you to guess passwords, wrong passwords, but only one wrong password every 10 seconds, but forever. Whereas the counter will basically say, after 3 wrong guesses, we're done. I'm not talking to you anymore.
And that's how it's done today, actually, in
Right.
French passports.
Right. This would basically say, or will rate limit you, like you said. Just sort of say you slow down. As long
You can just destroy a passport.
I'm sorry?
You can just destroy a passport remotely.
Well, actually, I have a picture of I think I have a slide on the French passport. No, not here. Sorry. I don't have the French passport right here, but the French passport, the way it works is after you make, until you've made a correct query, it introduces an artificial delay in its response time, but it doesn't have a way to reset the delay. So it will continue to delay you forever until you get a correct answer. So that's how they implement it today. There's no sort of back-off notion. There's no notion of time.
It seems another way you could do this is, well, suppose NIST or some entity with a lot of bandwidth was willing to answer questions in the form, what time is it, and would sign it. If you had such an entity and all your readers were online, you could rate.
Don't they have this service?
Okay, well, if that service exists, then what you could do
But how
is,
do you know that? Well, okay.
so you keep track of the last time that you were asked to charge or whatever, and then anytime somebody asks you to do something else, they have to prove that the current time is. They tell you what the current time is, and it has to be 12 seconds more than the last time.
I think there may be a little bit of a sort of circular argument, though. So that the proposal is you use a trusted third party to give you a signed time saying, it is this time, here's the signature. But don't forget, you need to guarantee freshness of the signature. And how do you guarantee freshness of a signature? You have a clock. But there is no clock to be able to guarantee the freshness.
I see. So if the adversary can guess you haven't used your card in the last 12 days, he can start with 12 days ago and play for it.
Yeah. So it's a real catch-22, and ultimately what it comes down to, and like Ross Anderson and Bruce Schneider talk about this, that ultimately you need a trustworthy clock. At some point, you just need physical security. And here we're trying to give you some physical security with a physical clock that comes at no cost. In other words, you've already paid for it because you're already draining your battery. And we're going to use that draining your capacitor. We're using that drain as a way to measure, just like a water clock would, or an hourglass. Okay, but I guess I'll stop there. Be happy to take any other questions offline, or if you want to know more about puffs, I've got more material on that. So, thanks.